On page 89, for the next example, pretty much everything on this page is a review or something we talked about in the first video. So remember that sometimes we use x to represent position when a particle is moving along the x-axis, but oftentimes we'll use the letter s. So if s represents position, then remember that the derivative of position is velocity, and the derivative of velocity is acceleration. So it follows that the second derivative of position is acceleration. So just a quick review. So these first two topics we first talked about in, Unit 5, that displacement, when we integrate velocity, we get the change in our position, which is displacement. However, total distance traveled, we have to integrate the absolute value of velocity. That gives us total distance traveled. A future position, again, this is just the first fundamental theorem, so we could use that formula. And then average velocity. So I mentioned this earlier in the last example. Since velocity is the rate of change of position, we could either find average velocity by integrating velocity and dividing by the difference in our limits of integration. So that's like what we did at the very first example at the start of the first video. But because of this relationship, because velocity is the rate of change of position, I could think of this as what is the average rate of change of position. And that's the average rate of change of S. So this is equal to the average rate of change of S. And again, like, if I think about that, it should make sense. I mean, I wish I hadn't said that. That was silly. Anything we think about should make sense. Okay, so actually, remember real fast that just this part, I'm going to write it back so don't erase it. We said that this is our change, S of A. This represents our displacement or change in position. So when I multiply this by 1 times B minus A, that's the same as dividing the left side by B minus A. I could do it to the right side as well. So that just kind of proves that last statement. Okay, we're going to do this example. And even though we could do this one without a calculator, I want us to practice using the calculator for this. You are traveling on a straight path from time t equals 0 to t equals 10, where t is measured in hours. The velocity of the car at any time t can be modeled by v of t equals t squared minus 6t plus 8, where v is measured in miles per hour, and the starting position of the car is 5 miles. So since our starting position is the position at t equals 0, I'm just going to write S of O equals 5. All right, so if we want to find the acceleration of the car at time t equals 2.5, let's go ahead and say this is also an FRQ exemplar, meaning I'm showing you exactly what I want to see when you show your work and you use a calculator. So first of all, AP and me, I will not assume that you know this relationship up here. You have to state this. So we have to somewhere, if we're asked about acceleration and we're working with velocity, we have to first show that the derivative of velocity is acceleration. So what this is really asking for is if the acceleration at time 2.5, we need the derivative of the velocity there. So in my calculator, I'm going to go to y equals, and I'm just going to clear out these equations from before. And I'm going to type in my velocity function. So t squared, it's going to be x squared, minus 6t, or 6x in this case, plus 8. And I'm not going to worry about graphing this one. So if we want that derivative, I'm going to go to second mode to quit. And the thing that we just stored, and I'm just going to write this out to the side, in y1, we just stored velocity. I'm not going to write that in my problem. AP will not acknowledge that calculator notation. So I'm going to go to math. And math 8 is n deriv, meaning the nth derivative. Well, meaning the derivative at a value of n, not actually meaning the nth derivative. So I want to pick math 8. On the new operating system, it looks like how we express a derivative. So d dx, using the variable, my derivative is stored in y1, so vars y-vars function y1, and I want to evaluate this derivative at 2.5. So I plug that in and I get -1. So a of 2.5 equals -1. Since we have units, we should use them. So that would be miles per hour squared, or miles per hour. And then to answer the second question, we need to find the velocity. So really fast, just out to the side, for those of you with the old operating system, meaning it didn't look like mine when that came up, for the derivative, you're still going to do math 8, and that should be n deriv. And it's going to prompt you with this, and you're going to have open parentheses. So let's see. I believe that the first thing you're going to do is type in the function. So if you stored your function in y1 like I did, you would go to vars, y-vars, function y1. You could type the function in every time, but like I would not recommend that. We're going to want it in y1 most likely. Okay, then we would separate that with a comma. The next thing that you type in is the variable with respect to which you're taking the derivative, which I'm not really sure why it asks you to do that because it's always x. And then lastly, you type in the value at which you wish the calculator to evaluate the derivative. So in our case, that's going to be 2.5. So it goes function, variable, value. Function, variable, value. Sorry, I'm just reading my notes. Again, you can always Google this. Like if you Google how to use TI, graphing calculator, find a derivative, old operating system, there's videos, there's websites, there's screenshots. All right, so that's how you would get -1 miles per hour squared. The second question though, is the car speeding up or slowing down? So remember, a car or any particle is speeding up when velocity and acceleration have the same sign, slowing down when the signs are different. So we need to find v of 2.5 as well. So in the calculator, remember we stored v in y1. So I can go vars, y-vars, function y1. The calculator knows function notation, but we must use parentheses. I have no idea what it does, but it comes up with some other number when we don't. We get -0.75, 75 100ths, and we know that is in miles per hour. Okay, so is the car speeding up or slowing down? Well, the car is speeding up. And we always have to say why. So we could say because velocity and acceleration have the same sign, or I could say like v of 2.5 is less than 0 and a of 2.5 is less than 0. All right, part B, what is the average velocity? So like the harder way to do this is we could find an antiderivative of v and do average rate of change. The easier way is to just use the average velocity equation. So the average velocity of a car on the interval from 0 to 10 is going to be 1/10, so 1/10. The calculator knows the order of operation, so it will do 1/10. And then we want to do times, and then I want my finite or definite integral, so math 9. and then I'm going to type it in. So from 0 to 10, and then again, my variable, or my function rather, is stored in y1. Okay, so again, you're not going to write this, like you're never going to write y1. You're going to write 1 over 10, or 1 over 10 minus 0, and we're going to write v of t. And then that gives us 11.333. Another thing that I think is silly, but don't do it, don't use a repeating bar, even though it is more precise. Even though 11.3 repeating is more precise, do not do it. I don't know why, but the College Board won't accept that as your answer. It's ridiculous, I know. All right, that is the average velocity. And since velocity is measured in miles per hour, we should express that as well. Part C, we are asked to find both the car's displacement and the total distance traveled. So displacement is going to be from 0 to 4, the integral of velocity. Total distance traveled is going to be from 0 to 4, the absolute value, or integrating the absolute value of velocity. All right, so in the calculator, I'm going to go to Math 9. Again, 0, 4 is my upper limit. Vars, y vars, function y1, and then x. All right, so my displacement is about 5 1/3. Oops, that's going to drive me crazy. Again, I'm not using a repeating bar. I wouldn't use a mixed number either. Just use the decimal, but take it out to 3. 5 1/3, and remember that is in miles. To do total distance traveled, we can start this off the same way. Math 9, our limits are from 0 to 4. But when I get to my integrand, I need to go to Math, then go over to Number, and the top thing is absolute value. In the new operating system, it makes the bars. In the old one, it says abs with parentheses. And in the old one, in the parentheses is where you would put your y1. Close your parentheses when you're done with that. All right, so the total distance traveled is 8 miles. All right, so lastly, part D. What is the position of the car at time t equals 6? And we can only answer this question if we know the position of the car at some other time, which we do. We know that the position at 0 is 5. So let's write it out first. The position at 6 is going to be the position at 0 plus the change in position from 0 to 6. And the change in position is displacement. Okay, so we said S of 0 is 5. All right, so in the calculator, we could do 5 plus Math 9. Let's see, 0 to 6. Vars, y vars, function y1. Always a dx there. 17 miles. All right, so the position of the car at t equals 6 is 17 miles. All right, that's it.